Hey everyone, it's me, someone unexpected. I've been learning a lot about physics recently, particularly about electricity and nanotechnology, and I want to share with you what I've been thinking about the last couple of days in regards to the potency of the electrostatic force, what makes it so different at the nanoscale, and how this will be useful in devising future nanoscale machines. Now, I'm assuming that the people watching this video already know what the electrostatic force is. Most people think that the electrostatic force is a weak force, because at the macroscale, it is a weak force. If you charge a balloon by rubbing it against your head, you can barely pick up a piece of paper with it. Yet at the nanoscale, the electrostatic force is one of the strongest forces in nature. It is the force that holds atoms and molecules together. The reason why the force is so weak at the macro scale is because the force obeys what is known as the inverse square law. The strength of the electrostatic force is proportional to the strength of the charges, and inversely proportional to the square of the distances between them. This means that if you double the distance between the charges, the force between them is 4 times as weak. But if you halve the distance between the charges, the force is 4 times as strong. From this, we can predict exactly how strong the electrostatic force is at the nanoscale. Let me walk you through a thought experiment that is meant to show you just how strong the electrostatic force is at the nanoscale. Let's say we line up 2 sheets of aluminum foil so that they are parallel, and we separate them by a distance of 1 millimeter. You can charge them so that the force between the aluminum is 100,000th of a newton. That's enough force to accelerate 1 gram 1 centimeter per second per second. Not a very strong force. You could probably achieve this with a regular 9 or 12 volt battery. But if you shrink the distance between the plates down to 1 nanometer, then you are decreasing the distance between them by a factor of 1,000,000. Which means that according to the inverse square law, if the charge remained constant, the force between the plates would increase by a factor of 1,000,000 times 1,000,000. That's 1 with 12 zeros after it. If you multiply that by our 100,000th of a newton of force, you get 1,000,000 newtons. 1 newton can accelerate 1 kilogram 1 meter per second, and the average person weighs little over 75 kilograms. So with that amount of force, you can accelerate 13,000 people 1 meter per second, unless they're Americans. This is not to say there aren't many practical limitations to building devices with this amount of power, but it should give you an idea as to how strong the electrostatic force actually is. With this, I have devised a theoretical nanoscale actuator. Now, I don't know how well this would work. Of course, I'm not an engineer. I'm using it as a way to show people what kinds of machines could be built at the nanoscale, and how they might work. Anyways, this is the actuator when it is uncharged. It is made of 2 strips of a material called graphene, right here, illustrated right here. Graphene is a 2-dimensional carbon lattice that conducts electricity. The strips are linked here and here so that they can't move or slide past each other. Here is the device when it is charged. Like charges repel each other, which causes the 2 strips to move apart, thus causing the entire device to contract like a muscle. So with this I end my little diatribe about the electrostatic force and nanotechnology. Bye!